In question 78, you're required to calculate the molarity of the solution. In this question, you're going to use the formula molarity is equal to moles divided by the volume in liters. In the question, you've been given the number of moles as 0.02 and the volume as 200 ml. We need to convert 200 ml to liters. So you're going to use the relation 1 liter is equal to 1000 ml. So if 1 liter is 1000 ml, what about 200 ml? You're going to do cross multiplication, then you're going to come up with 0.2 liters. Then you substitute in the formula whereby molarity is equal to moles divided by the volume in liters. So molarity is going to be equal to 0.2 moles divided by 0.2 liters, which gives you 1 molar. In question 79, you're supposed to obtain the final concentration in the 1000 ml flask. You're going to use the formula M1V1 is equal to M2V2, where M1 is the molarity of sodium hydroxide, which is 8. V1 is the volume of sodium hydroxide, which is 250. M2 is the final concentration that we don't have, which you need to calculate. And V2 is the final volume after dilution, which is 1000 ml. So the sodium hydroxide was diluted from 250 ml to 1000 ml. So after diluting from 250 to 1000 ml, we are supposed to get the new concentration. So we're going to use the formula M1V1 is equal to M2V2. So we substitute in the formula where M1 is 8, V1 is 250 ml, M2 is what you're looking for, and 1000 is the volume after the dilution took place. So when you work this out, you're going to find that 250 goes here once, 250 goes here 4 times. So 4 goes there once, 4 here twice. So M2 is going to be 2 molar. In question 80, we're supposed to identify if hydrobromic is an acid or a base. According to Arrhenius theory, an acid is any substance that releases hydrogen ions in solution. Hydrobromic acid is an acid because it contains the hydrogen ions. So these hydrogen ions can be released into a solution. So by virtue of having the hydrogen, we call it an acid. Next, sodium hydroxide is going to be a base according to the Arrhenius theory because it has the hydroxyl ion. So a base is any substance that releases the hydroxyl ion in solution. Sodium hydroxide is a base because it contains the hydroxyl ion. Question 82. According to the Bronsted-Lowry theory, we need to identify if ammonia is an acid or a base. So according to the Bronsted-Lowry theory, any compound that can transfer a proton to any other compound is an acid. And the compound that accepts the proton is a base. In the question now, you can see ammonia accepts to combine with the hydrogen ion to form ammonia ion, which is here. Thus, we could say ammonia is a base because it's a compound that accepts the proton. So ammonia accepted the hydrogen. Question 83. We have the equation hydrogen cyanide plus water to form the hydronium ion and the cyanide ion. So in this question, hydrogen cyanide is an acid and it contains hydrogen ion. So this is the hydrogen ion contained by the hydrogen cyanide. A conjugate base is formed when the hydrogen ion is removed from an acid. If you take away this hydrogen ion, you're going to remain with only Cn ion. And this Cn ion is what we call a conjugate base. Thus, we can conclude and say that hydrogen cyanide is an acid and CN is its conjugate base. Question 84. We're supposed to identify whether hydrochloric acid HCl is a strong or weak acid. We've been given a list of strong acids, that's HCl, hydrobromic, hydroiodic, and nitric acid. Weak acids, hydrofluoric, hydrogen cyanide, and carbonic acid. So HCl has been listed as a strong acid, so that makes it a strong acid. Question 85. We're supposed to identify whether ammonium hydroxide is a strong or weak base. In the list of strong bases, we have lithium hydroxide, rubidium hydroxide, and barium hydroxide. In the weak bases, we have ammonia hydroxide and ammonia. So definitely, ammonia hydroxide is a weak base. Question 86. Sodium hydroxide is a dash base. So the strong bases we have are lithium hydroxide, sodium hydroxide, barium hydroxide. The weak bases, ammonium hydroxide and ammonia. So sodium hydroxide is listed as a strong base. So we're going to take option A as a strong base. Question 87. We are supposed to write the net ionic equation for the acid-base neutralization reaction. Hydrobromic acid plus potassium hydroxide to give potassium bromide and water. Hydrobromic, potassium hydroxide, and potassium bromide are aqueous solutions. That means they can dissociate into their respective ions in solution. Hydrobromic acid contains hydrogen and bromide ions. Potassium hydroxide contains potassium and hydroxyl ions. Potassium bromide contains potassium and bromide ions. So the equation can be written as hydrogen ions plus the bromide ions plus the potassium ions plus hydroxyl ions gives potassium ions plus the bromide ions plus water. Then, after writing this equation, you're going to look on both sides of the equation to see which ions are common in both sides. The first one is bromide. There's also a bromide on this side. Potassium, there's another potassium on this side. So these ions are going to cancel out. Then we remain with the hydrogen and the hydroxyl and the water, which was in liquid form, and it's molecular, so it cannot dissociate into its respective ions. So the final equation will be hydrogen plus hydroxyl to form water. Question 88. We've been given a 0.01 molar hydrochloric acid solution. So we're supposed to write that concentration in standard form. To write 0.0100 in standard form, you're going to move 2 steps to the right from the decimal point. So you move 1, 2. So the second step is up to where there's a whole number. So you're going to have this as 1.0 times 10 power negative 2 because you moved 2 steps to the left. So to the left, you have to use the negative sign. Thus, 0.0100 can be written as 1.00 times 10 power negative 2. Question 89, you're supposed to calculate the pH of 0.001 molar hydrochloric acid solution. To calculate the pH of an aqueous solution, you need to know the concentration of the hydronium ion. The hydronium ion is formed when an acid is added to water, whereby hydrogen ion in the acid breaks away from the acid and combines with the water molecules. The pH is calculated by taking the negative log of the hydronium ion concentration. The formula for calculating the pH is given as pH is equal to negative log times the concentration of the hydronium ion. This is hydronium ion. From the question, the hydrochloric acid solution has a concentration of 0.001 molar, which can be written in standard form as 1.0 times 10 power negative 3 m. Substituting in the formula, we have pH is equal to negative log 1.0 times 10 power negative 3, and when you put this in the calculator, you're going to get the answer as the pH of 3. So that's our answer up there. Question 90. We have 0.001 molar sodium hydroxide solution, and we expected to calculate its pH. Remember, sodium hydroxide contains hydroxyl ions, so it's a base. Therefore, the formula for calculating its pH is given as POH is equal to negative log times the concentration of the hydronium ion. The concentration of the hydronium ion, according to the question, is 0.0100 molar. When you write this in standard form, you're going to have 1.0 times 10 power negative 3. So when you substitute that in the formula, you're going to have POH is equal to negative log times 1.0 times 10 power negative 3, which gives you the POH as 3. But remember, pH plus POH gives you a sum of 14. Since our question required us to get the pH, and we have already got the POH, you're going to do substitution in the formula, whereby pH plus 3, which is our POH, equals to 14. pH is going to be equal to 14. 3 goes to the other side, minus 3. So pH is 11. Question 91. We're supposed to obtain the concentration because we've been given the pH. In this question, the pH is given and we are required to calculate the concentration of the solution. We have been given a conditional clause where we've been told that concentration of the hydrogen ion is equal to 10 power negative pH. So that is the statement or the condition that you're going to use to obtain the concentration. So we'll use this as our formula, and where pH is, we're going to replace it with the 4.74, and our equation is going to become like this. Concentration of the hydrogen ion is equal to 10 power negative 4.74. When you work that out, it gives you 1.8 times 10 power 5 molar as the concentration of this solution. Question 92, we're supposed to identify which statement is incorrect. Statement A says the number of hydrogen per molecule in H3PO4 is 4. But if you look here, the hydrogens are 3. Here the hydrogens are 2. Here the hydrogen is 1. Here the hydroxyl is 1. And here there are 2. So statement A is then correct by saying that there are 4 hydrogen instead of saying 3 hydrogen. Question 93. We are expected to use the relation VA times number of hydrogen per molecule times molarity A is equal to VB times the number of hydroxyl per molecule times molarity B to obtain the missing volume of barium hydroxide. So this is going to be our formula that we're going to use to obtain the volume of barium, which is volume B. So you'll write it like that. Then after writing it like that, you're going to do the substitution. Volume A is the volume of phosphoric acid, which is 20 ml. 3 is the number of hydrogen ions times molarity A, which is given as 1, will be equal to volume B is what you're looking for times 2, the number of hydroxyl ions in barium hydroxide, times 1, which is the molarity of the barium hydroxide. So when you work this out, you're going to have the volume as 30 ml. Question 94, we've been given some information there that alpha particles can be stored by paper. Beta particles can be stored by 0.5 centimeter thick lead plates, while gamma can be stored by 10 centimeter lead plate and a thick concrete. Then alpha particles are basically helium particles, which are positively charged particles, can be stored by, so we have already seen up here, they can be stored by paper. Question 95, alpha particles can be stored by paper, beta particles can be stored by 0.5 centimeter thick lead plates, and gamma can be stored by 10 centimeter lead plates and a thick concrete. So beta particles are electrons which can penetrate paper but cannot penetrate. So beta particles cannot penetrate 0.5 thick lead plate. Question 96, we've been told that gamma rays can be stored by 10 centimeter lead plate and a thick concrete. Then the gamma rays are rays which can penetrate 0.5 thick lead plate but cannot penetrate 10 centimeter lead plate. Question 97, we're supposed to identify the incorrect statement as far as the question is concerned. The first thing we're going to do is to equate the superscripts. Superscripts are these numbers which are at the top. So the numbers at the top are 238, there's an equal sign here, is equal to A plus 4. So when you work this out, A becomes 234. So this statement is correct. For B, 92 is going to be equal to B plus 2. So B is 92 minus 2, which is 90. So this other one is also correct. So the incorrect statement is that one there. Question 98. Which one of the following statement is incorrect about beta emissions? Also in this case, again, we are going to equate the superscripts, the numbers which are on top, and also in the second instance, we equate the numbers which are at the bottom. We call them the subscripts. So starting with the superscripts, 234 is equal to C plus 0. So C is 234. So this one is correct. When we equate the subscripts, we have 90 is equal to D minus 1. So 90 is D plus 1, which is 91. So D is equal to 91. This one is also correct. So the statement D is 89 is incorrect. Question 99, we're talking about half-life. Half-life is the time taken for a radioactive substance to reduce by half of its original or initial value. So if you look at this table here, at 0, the value was 100. So the value for this value to reduce by half, it means it has to reduce to 50. So it took how many days? 2 days. So the half-life becomes 2 days, because it took 2 days for this substance to reduce by half. Finally, question 100, you're supposed to identify the number of radioactivity after 4 half-lives. So let us count the half-lives. That's the first half-life, the second, the third, and the fourth. So the radioactivity is 6.25 after 4 half-lives.